All right, good afternoon, everyone. We have to finish, or you have to finish homework for today, right? So, do you have any question about problem number 6? Problem number 6 is the problem in which you have to calculate fracture half length, width, and net pressure as a function of time. Did you all solve that one? Do you need any help with that one? No? Speak now or...
Do you want it?
Yes.
Do you just want the equation or you want like a graph?
No, I want a graph. I want something like what I'm going to show you right now. I want something like this, okay? In which, wait, what did I do? Okay.
No.
I want something like that, in which, as a function of time, you tell me what is fracture length, fracture width, and fracture net pressure, okay? I think that one is relatively straightforward, and although you have to solve that one with a computer, I strongly recommend that you try to solve by hand, let's say the last point, verify by hand, because in the exam you may have to do this by hand, okay? So verify the last point and make sure that you know how to use those equations. Yes?
On the homework it's 1 hour or you want 30 minutes?
This is a different one.
Oh, okay.
This is a different one, yeah. But it's similar to this one. Okay, so if there are no more questions, we'll go to number 5, which involves computing or determining the fracture height. So how are you guys doing with that one? More or less done? Yes, I want you to plot everything that what you have over there, okay? So there you will realize how the plane stress modulus affects stresses. So, okay, for those of you that are not super advanced on this particular problem, let me give you a few hints. So the yellow columns are the data, okay? Depth, column A, reservoir pressure or pore pressure, column B. So this is pore pressure, column B. Then you have mass density, compressional slowness, and shear slowness. How do you determine compressional slowness and shear slowness? Yes, and then, but how do you actually do that? You may have to answer that to Professor Torres Verdi. What kind of sonic? What tool? Dipole, right? This is not most conventional tools. They just measure P, but to measure S, you need an additional feature in the tool. So not all well logs have shear. If you want to determine the Young-Morrison and Poisson ratio, you need both. And there are some other tools that permit measuring shear velocity in different directions. And from that you can infer also the anisotropy of the rock, the anisotropy in the elastic properties. But now we'll just stick to BP and BS. Okay, with those you calculate BP and BS. Here you have the formula to go from feet to feet and microseconds to meter per second. BS is the same formula. You have porosity too. In this example, you don't need porosity, okay? So don't worry if you don't use porosity. Using the equations of elasticity, you compute Poisson ratio and Young modulus. So you may say, oh, where did those equations come from? And those equations, you saw those in petrophysics. The P wave velocity is equal to the square root of the constraint modulus divided the mass density of the rock. And the shear wave velocity is the square root of the shear modulus divided the mass density. If you combine those equations to the qualities that we have seen between constraint modulus and shear modulus together with Young modulus and Poisson ratio, you can get these equations. Poisson ratio and Young modulus. Okay? And you can also compute what is this Poisson ratio divided 1 minus Poisson ratio. What is that factor? No. Poisson ratio divided 1 minus Poisson ratio. We have used this quite a bit.
Is that E plus L?
No. No.
E prime, is that E prime?
No. Poisson ratio, look, is Poisson ratio divided 1 minus Poisson ratio. What are the units of that? No units, right? So it's not the modulus. Poisson ratio divided 1 minus Poisson ratio is the coefficient of lateral stress. You remember that we derived that sigma h was equal to Poisson ratio 1 minus Poisson ratio times sigma b. That's the amount of stress which is transferred laterally by a vertical stress to horizontal stress.
That's the easiest way to calculate the SH.
No, that's one component, right? Because once you get the Poisson ratio and you get the plane strain static modulus, I notice here that I added a 0.65. So this is 0.65 times E divided 1 minus Poisson ratio squared, where the 0.65 is a conversion value from dynamic to static, a value which is always less than 1. So you use this value and that value, and together with the vertical stress and the pore pressure, and you can calculate here, for example, the maximum horizontal stress. All right? So let's try to read this equation. This is pore pressure, okay? Because we want to calculate the total stress, so I am adding pore pressure. B3 is pore pressure. What is O3 minus B3? So, effective vertical stress, right? That we multiply times this coefficient, Poisson ratio divided 1 minus Poisson ratio. And to that we add N3, where N3 is the plane strain modulus times what is 0.0015 in this case. That is the tectonic strain, this value. The tectonic strain, and because the other one is 0, the equation here is simplified. There is one term less than before. And notice that this one is for SH max. For SH mean, in addition, we need to multiply times the Poisson ratio. So you do all of this, and then you have all the stresses as a function of depth. Something that, let me clarify too, if you didn't get to this point, I give you data starting at 1,750. Guys, please be quiet, okay? What is going to be the initial value of vertical stress? Do you think it's going to be 0? No, right? So what I have done in this case, I have assumed that everything above this depth has the same mass density, so it's just the gradient with that mass density times depth. And that gives you this value, and for the additional values, I add the previous value to the additional stress due to the weight of each layer as we move down. And so you have vertical stress, you have pore pressure, and then now you can calculate the horizontal stress as a function of depth. And this is an additional calculation, is the pore pressure parameter, right, which is going to be pore pressure divided vertical stress. And then you can plot mass density, vertical stress, the slowness, plane strain modulus. And what you should notice here is that how the plane strain modulus has a direct effect on the horizontal stresses. Where the rock is stiffer, like here, there, or here, you're going to see that your stress is going to be higher at those locations. So basically, all of this covers 5.1, 5.2, 5.3, 5.4, 5.5, and up to 5.5. Any questions so far? Yes?
I did not quite understand how you calculate the vertical stress.
So the vertical stress, I need to assume what is the initial stress at the beginning of the data, at that value, okay? So what I do is I assume that everything above has that density. So I took a shortcut here because what is the gradient in PSI per foot for that we use all the time? 1 PSI per foot, right? 1 PSI per foot corresponds to a rock weight. If you check to at the beginning of the lectures, that corresponds to a rock that weighs 2.3 grams per centimeter cube. So here I just divide the actual value divided 2.3, and that's going to give me already the gradient in PSI per foot, but for a rock which is lighter than 2.3. And you multiply that times depth, and it gives you exactly the value of the vertical stress. If we had a rock that was 2.3 grams per centimeter cube, this initial value should be 1750 psi. But because the rock in this particular place is lighter than that, the stress is not as high as that. So that's the initial value. And after that, it's just adding the weight of each layer. All right. And basically the trapezoidal rule for integration. Any other question about this part? Yes?
So for the total stress below the 1750 feet, do you also use the density, like, it's like below, we have the data for the density of the rock below
Yes.
1750 feet, right?
I use the actual density. Notice in this equation that I'm taking the average. Probably it's kind of small to see over there, but let me see if I can zoom in. I'm taking the average of C is a column of mass density, so I'm taking the average of that mass density in that interval, and I divide it again by 2.3. So I'm accounting for the actual density of the rock. And this is difference in depth. So that gives me the additional weight that I need to add to the previous value.
What's the C for?
Mass density. C column is mass density. A column is depth in feet, C is in grams per centimeter cube. Yes?
Did you do something similar for SH max and SH min, like take the average and add it to the previous one? Or
No, because SH max and SH min, they just depend on the vertical stress at a particular depth and the tectonic strain and the plane strain modulus.
Okay.
So
Yeah, just come.
I don't use any average anymore. All right, so then you're gonna get to this point, and then you're gonna get a plot that looks something like this. All right, and here in the problem statement, it tells you. Let me put this on the side. The problem statement tells you that the pay zone is between 2500s and 2450. So between here and 2450. Let me change these to 25. Somewhere around there. So 21 and 2450. That this is a pay zone, all of that. And then it tells you that a fracture is going to be started at this depth. That means that perforations are going to be placed at the depth between 2130 and 2160, which is somewhere around here, right? 2130, 2160. So the question now is, what is going to be the fracture height first, and second, if that fracture will reach out to the entire pay, which is, so all of this is entire pay, more or less up to there. So what do you think? That's entire pay.
No.
Why not?
It has to do with gravity, and the fracture won't propagate upward as high as it will down as it goes down.
What do you mean with the gravity?
Well, it's trying to fracture against gravity if it's going vertically. But then
So your fracture is starting over here. So what is the blue line? Which is stress? Minimum horizontal stress. The green is maximum horizontal stress. And the red is vertical stress. Let's start with a simpler question. What is the faulting regime at the depth of the perforation? So again, we say 2130, 2160, let's say there. This is the region where we have the perforations. It is what? Normal, right? SH min, SH max, SV. So, if you were to start a fracture somewhere at this location, the fracture is going to be already at the local minima, or minimum in this case, of the minimum horizontal stress. So, as we know, fractures like the minimum principal stress, so it will tend to stay in this region. Why? Because this is the region in which we have the lowest minimum principal stress. And from this plot, it looks like actually it will tend to propagate down because this horizontal stress is the lowest at this point. Everyone follows me up to here? Okay, the next point is to determine if the fracture is going to overcome those stress high values or not. What do you think this is going to depend on? Let me change this number while you think about that. Any suggestion? Will the fracture overcome those stress humps or not? Okay. So, if the stress, what should be, let me change the question. What is going to be, or what should be the net pressure in the fracture in order to, the minimum, in order to go over these high stress values? The lines are spaced every 200 psi. Like about 300 psi, right? If your net pressure is higher than 300 psi, probably you need a little bit more to actually open the fracture, but the stress or the pressure in the fracture is going to be high enough to go over these values. But if it's less than that, you're just going to stay in this region because it cannot go over that value of stress. And in that case, your fracture height will be more or less from here to there, which is how many feet? From here to there? 100 feet, right? If your net pressure doesn't overcome that value, it will not reach to the entire pay zone. If you really want that stress or that fracture to overcome or to go to the entire pay zone, probably the best idea here would be to do more perforations somewhere around here, because otherwise you need a net pressure which is going to be too high, and probably if you increase too much the net pressure here, the fracture is also going to go up instead of to go down. Okay, everyone agrees with that. So fracture height, more or less 100 feet if you do not overcome this value of the net pressure. And probably it won't reach the entire pay. If it does, you need, or if you wanted that, probably you need additional perforations lower in the vertical wellbore. Okay, now let's try to see what do you think it will happen if we had a slightly different, so this is not part of the homework anymore, but it's for us to think about that, okay? In all these cases, except at this small location, it looks like always we have either normal faulting, or for example here, what is that stress regime? Strike slip. The hydraulic fracture is going to be still a vertical plane, but let's change something over here. Let us change a little bit the tectonic strain. Let's see what we get. Let's see, that was enough. Not much. Let me increase it a bit more. Strike 8. Okay, I got to the value I wanted, but probably a bit more will make it clearer. So I'm just changing the tectonic strains. If I increase the tectonic strains, what's going to happen with the horizontal stresses? They're going to increase too, right? All right. So let's continue with the same logic. We start a fracture over here, and suddenly we get to this point. What is the faulting regime here at 2100 feet of depth? Inverse. What do you think is going to happen with the fracture? With the fracture geometry? So, anyone has an answer? Yes.
If you have a horizontal well, will it just propagate sideways from the well? It's opening against the bottom stress, which would be SB.
And then what is going to happen with the fracture?
It'll propagate on the sides of the wellbore.
On the size of, it's going to be perpendicular to what?
SV.
SV. So, in that case, that is what is called a T-shaped fracture. And this is a side view. It is start as a vertical fracture, but then when it gets to a change of the faulting regime, it will start to propagate like that. That's what it looks like, a T, right? That's what it's called, a T-shaped fracture. And sometimes, that can be good because it's good for fracture containment. But imagine if you have a lot of your fracturing fluids into this location, probably that's not where you want them to go. So this occurs when there is a reversal of the stress regime. These type of fractures also happen in nature. Usually in nature, when you have vertical hydraulic fractures, those are called dikes. When you have horizontal hydraulic fractures, which is just basically lifting the ground, those are called seals. S-I-L-L. Yeah?
How are you looking at this? How, this side view?
Say again?
How do you look at it from the side view?
So to be clear, I'm trying to line up this now with the formation, okay? So in this region, it appears, well, let's further assume that the fracture just grows up to here, okay? The perforations in this vertical wellbore were somewhere over here. So it starts growing vertical in this region, okay? And then it gets to this change of stress regime, and then it flips. So this is side view, and in this direction this is up, right? So I don't know if this is clear enough, but if you want, I can try to make a 3D view of that. So with something like this. Something like that. So when it gets to that top formation, it changes direction. Yeah?
Which way is SH bend?
Well, SH mean is going to be always in the same direction. This is SH mean. And thank you for that comment, Mr. Wheeler. That helps a little bit clarify what's going on. So in this location, S3 is SH mean, but here at that location, S3 is SV. That's why. it changes direction. All right, so what's the takeaway message from this? I want you to be able to read these stress logs. I want you to be able to tell me if I were to start a hydraulic fracture in any location, what's going to happen to that hydraulic fracture. I mean, it may not be super accurate at this point, but you have to know what are the implications of the variation of stress with that. And if I gave you something in the stress log which is already calculated, you should be able to interpret that. Okay? So basically this is the end of that homework. Yes?
Can you use this to kind of like determine what places you would start, what depth or what interval you would start your fracture with?
Yes. And this is what you use as an input in the hydraulic fracture simulator to tell you exactly what is going to be the shape of the fracture.
So would you choose where like your SH main is lowest?
Say again?
Would you choose that interval where your SH main is lowest? Or you can't just
Yes, here. If I had to do perforations, probably I would go around here. Okay.
I just have one
Yeah.
question. What was lambda on the data? I saw a lambda column. I'm not sure.
Overpressure,
Okay, gotcha.
it's pore pressure divided vertical stress. Okay. I see that many of you are with your computer, so probably you can try to get this solution on your own, and we can do that for about 7 minutes, and then I talk about a little bit about the homework due next Friday. Okay? Yes. Well, you know, it says, at each one it says calculate your module of ratio. I like it. When I say calculate, you don't calculate it. No, I'll refer to it. No. All the things that are not
Whatever you visit for next
All right, guys. I see that most of you are done with that. So if you have any questions, just please let me know, or Muhammad will help you with that. Any question now about that problem, or it's okay? Yeah.
So still the number 5, question 1 of number 5, asking to compute the overpressure parameter. That so in order to calculate that, we need like a pore pressure data, right? And the pore pressure data is the reservoir pressure, But
Where do they ask over pressure? I don't think I do.
it compute the question 1, asking for compute the overpressure parameter?
Oh, yeah, there it is. Yes. Yeah, you're right. So it's pore pressure divided vertical stress. And if I say calculate something, I'd like that you make a plot of that to show that you actually did it, right? So in this case, I didn't plot that, but basically that would be this one as
Also, I calculate the parameter for every single class and then
so that's the lambda parameter. Okay? All right. So you have another homework due on Friday. So okay, let me tell you about the schedule for the rest of the class. We have lecture on Monday and Wednesday, and then I'll give you Friday off. Okay? So we're not going to have the lab in CMG. We're just going to talk about conceptual part of reservoir depletion. And for next week, you need to solve these other two problems, which are going to be the last two problems in the homework. This one is relatively straightforward. You have to go into the web to look for a stress map of North America. Here is a link, but apparently the guys took down the site, so it's not going to take you anywhere. Okay, I'm gonna modify this link, but if you want to go ahead with that, just type stress map North America, and there is an image from here, nap.edu, where you will find this image, which is at a reasonable resolution. And in this problem, it asks for designing a completion design on the Barnett shale. So Barnett shale, somewhere over here, okay? So you need to take stresses from this location and then do what is said over here. So you know what is direction of maximum horizontal stress. Remember, that's maximum horizontal stress. And then with that, you have to do a schematic about what would be the direction of the wellbore, the spacing between stages, and you also have to calculate what would be the pressure needed to open up the fractures at that particular location. So basically you have to calculate the minimum principal stress. And then this is just an exercise from deviated wellbores. You have to draw the path of that horizontal wellbore in a stereo net projection. Okay? The next one, it's a little bit more difficult and involves microseismicity. So let's talk 5 minutes about microseismicity. Probably I won't finish today, but let me check something over here that I want to make sure that if it's available for you or not. For some reason, yeah, I don't know, for some reason my computer also, I cannot see this figure 731. But let me tell you what that figure is. Are you guys familiar with microseismicity? What is microseismicity?
Earthquake triggers.
What? Probably, yeah, you can call it like that. And to be precise, what is the magnitude? Why is it called micro?
Less than 1 on the Richter scale.
Less than?
1.
Less than 1. I have less than 0 in my notes, so we'll stick to that. And in which scale? This will be in the Richter scale. So in this scale, for example, a very powerful earthquake has a magnitude of 6, 7, up to 8 or 9. And remember that this is a logarithmic scale, okay? So what that means is that an earthquake, for example, that has magnitude 6 is 1,000,000 times more powerful than a microseismicity with magnitude 0, okay? That's telling you order of magnitude. Well, recently in the field, we have been using microseismic monitoring, and in this case, this is a horizontal wellbore. And if we have hydraulic fractures, we most time expect to have planar fractures. Let's say that we don't have any fracture interaction in this case. Actually, nobody has seen these fractures in the field. You can get some evidence about more or less where they are going, but nobody has seen the fractures in the field. So up to now, this is just a conceptual image, an ideal image. Well, it happens that when you do this in the field, you get a lot of microseismic activity that is not exactly where you thought the fracture could be, but it comes from places which are further away. So what do you think is happening at all those locations? First, what is seismicity? What? A release of stress, right? But which kind of stress? There is some release when you break a rock in tension, but usually in tension, the magnitude of that emission is a lot smaller than the other one. So there is tension and then there is shear, right? Each of these points, and also with a major earthquake, what you have in a major earthquake is the faults reactivating one to each other, and that release of stress when the fault moves is what creates an earthquake. Well, in this case, it's very similar, but these fractures are a lot smaller than a big fault. And when this one, let's make them to have some asperity, when they move relative to each other, they release energy, and that energy converts into elastic waves that are released to the surface. And remember, this is shear failure. And how do we like to check when rocks fail in shear? With a Mohr circle. So basically, we have here the shear limit, and same as we have done before with faults, these small fractures have a characteristic principal value of stresses, and when you inject fluids, pore pressure and strains can cause this Mohr circle to move to the left and to reach the shear yield. When they fail, they emit microseismicity. We'll continue talking about this on Monday, okay? Have a good weekend, guys.